over the dimensional analysis homework with you. I understand that a lot of you had difficulty with this. It's a very abstract idea, very powerful idea, but it's abstract. And I think as freshmen, most of you aren't used to thinking in terms of the way physicists think. So let me give you some introductory information first, and then we'll go on to trying out some problems together. Okay? So before we do the problems, let me give you some background information. Okay, so when we talk about dimensions, we're going to talk about dimensions of physical quantities. Those are probably words that are very unfamiliar with you at this point. So let me write this down. Dimensions of physical quantities. Right? Now, what are physical quantities? What are physical quantities? Okay. There are many different types of physical quantities, but there are only a very small number of basic ones. So let me tell you what the basic ones are. And you can tell what the basic ones are based on what kind of measuring device you use to measure that quantity. Okay. The first device I bring up is a meter stick. Okay. A meter stick is used to measure length, and length is one of the basic physical quantities. All right, so let me write this down. Basic physical quantity okay. And one type is the length. And we use a shorthand, capital L, to represent length. Okay, and measuring device is like a ruler. Okay, we measure length with a ruler. Okay. Another type of basic physical quantity. What could you think of? Okay. I could think of, what's this? It's a stopwatch. Okay. I push this to start, push this to stop, or yeah, and then push this to clear. Right? So, a second type of basic physical quantity is time. Time. We represent that as a capital T, and we measure it with something like a watch or clock. Okay? What's a third type of basic physical quantity? What's this? It's a bathroom scale. Okay, what do you measure with a scale? Some people might say weight. A more appropriate term is mass. So the basic physical quantity we want to talk about here is mass. So let's write the third one down. Mass. Okay, and we measure it with a scale. Right? What else? What other type of basic physical quantity are there? There are actually quite a few others, but today I'm just going to stick with one more. And I'm going to show you, what is this? It's a balloon. Remember the first day of class, I rubbed the balloon on my hair, and somehow, magically, when I do that, the balloon sticks on the whiteboard. Why does it do that? Because of electric charge. And that's my fourth basic physical quantity. Okay, electric 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 charge. And the shorthand for that is the Q, capital Q. Don't ask me why it's a capital Q, but still it's charge. And then how do you measure it? Let's see. Erase this guy. How do you measure it? You measure it with like a balloon. Balloon, right? Doesn't look like an O here. Erase that a bit and fix that up. Okay. So these are basic physical quantities. Okay, and these capital letters represent the dimension of each of these. And now what I'm asking you to do is to take more complicated physical quantities like velocity and acceleration and determine what is the dimension of those complicated quantities in terms of these more basic quantities. Okay? So now let's go to the worksheet. Okay, so I just finished telling you about basic physical quantities. All right, and I told you that there were many, or not that many, there's a small number of basic ones, but I showed you just 4 of them because we only work with basically just 4 of those in freshman physics. Okay, the first one is length. Second is time. Okay, third one, mass. And fourth one, circle here, was electric charge. And we called it a Q, all right? So let me highlight, oh, didn't like that. Erase this. Use a red pen to highlight it. All right, the basic physical quantities. Erase that here. All right, so now I want to make more complicated physical quantities using these. So I want to build up more complicated physical quantities. Oops, what's going on? I want to use a black pen. Build more complicated you know what I mean, complicated physical quantities. Okay. All right, and I'll give you an example. Velocity. Okay, That's defined as distance traveled divided by time required. Right? So the question arises, what is the dimension of velocity? We know the dimension of length, time, mass, and electric charge. What's the dimension of velocity? That's a physical quantity that describes something that's happening in the world. Okay. Well, to find the dimension of velocity, we use this notation: square bracket v for velocity. That's the dimension of that is equal to the dimension of the numerator divided by the dimension of the denominator. What kind of quantity is the numerator? It's a distance, which you measure with a ruler, so it's a length. So we write L for the numerator. What kind of quantity is the denominator? You would measure it using a stopwatch or something. So it's a time. Okay, and the answer now is the answer is that the dimension of velocity is distance divided by time. Right? So basically, using the basic physical quantities, you could build up more complicated physical quantities. And I could tell you what the dimensions of these complicated physical quantities are. Okay? Does that make sense? A little bit? Okay? So now, let's try the problems. All right. So now, let's do. Yeah, it's recording. Sorry. Now let's do the dimensional analysis homework together. All right. So let's scroll this down. Okay. So question 1: what is the dimension of velocity? To determine that, we determine what is the dimension of the numerator and divide by what is the dimension of the denominator. Okay. What kind of quantity is the change in position? Position, well, you're talking about position, so position is measured using a ruler, so it's a length. So you put, let's see, we choose a black pen, we put an L here. How long it takes for something to happen? What measuring device do you use for that? You use a stopwatch. Okay, so it's L divided by T. Okay, acceleration. Okay, here the numerator is change in velocity. What kind of quantity is that? Well, the important keyword is velocity, right? So, what's the unit of what's the dimension of velocity? Well, we already did that in problem 1. So we bring over L over T. So this is work that we already did in part 1. So I'm bringing this from up here and bringing it down here. What's the denominator? How long it took something. That's measured with a stopwatch. So we divide by time. And if you're the math type, you can just leave it like that. That's valid. If you're the math type, you can simplify and realize that this is equal to L over T squared. Okay, because there's a T in the denominator in the numerator, and if you know your algebra, you know that you can bring that downstairs to the denominator. And call it L over T squared. But if you don't know that, don't worry. You're in Algebra 1 and you'll be learning about these things. soon. You'll learn about it soon. Okay. Force. Okay. What's the dimension of force? Well, let's look at the definition. Force is mass times acceleration. Okay. So, what was the dimension of mass? Was just m. Okay. So we do mass times acceleration. Okay. What's the dimension of acceleration? Well, we already did that upstairs in problem 2. So we reuse the result from problem 2. So we bring this down here and we write L over T squared. It doesn't look like a square, does it? Okay. And that's your answer. The dimension of force is mass times length divided by time squared. Momentum. Momentum is given by the force acting on an object times how long the force acts on the object. Okay. So, what's the dimension of force? Well, we already did that in problem 3. So we're going to use this result and bring it down here, and we're going to say it's m times L divided by n.
Good afternoon, Maryknoll. Here are the end of your day announcements. Any students interested in...
Alright, sorry for that interruption. So, momentum is equal to force acting on an object times how long the force acts. So, the dimension of force, we already determined that in problem 3. So, when you reuse the result, okay, and we bring down m L over T squared, and then you're multiplying that by how long it took. That's the dimension of time. How long it takes something is measured using a clock. So multiply by t, and if you're algebra type, if you're up to speed with your algebra, you realize that you can cancel out t upstairs with 1 power of t downstairs. So we can simplify that and call it m L over t, like that. Okay, so that's the unit of the dimension of momentum. Let's do number 5 together. Energy is defined as force acting on an object times how much the object moves, okay, in the direction of the force. Okay, so what's the dimension of force? Well, we already determined that in problem 3, so let's reuse the result. We don't have to redo all the work. We do m L over t squared. And now we're multiplying by distance. So distance has a dimension of L. And using algebra, you can combine L here with L here. And that gives you 2 powers of L. So you get m L squared over t squared. Right? That's the dimension of energy is mL squared divided by t squared. Hi. All right, let's continue. What's the dimension of pressure? Let's look at the definition of pressure. It's a force acting on a surface, okay, and divided by the area of that surface. Okay, so to find the dimension, then what's the dimension of force? That goes on the numerator. Well, again, we can reuse the result from number 3. So let's get a red pen. Use a red pen and write mass times L over T squared. Okay, that's the unit of dimension of force. And then we have to divide by the dimension of area. Okay. What's the dimension of area? Well, it's width times height. Okay. Width times height. Well, width is has a dimension of length. Height also has a dimension of length. So the dimension of area is just length times length, or length squared. Okay, so it's ml over t squared, the whole thing divided by l squared. And if you're good at algebra, okay, it's good enough to just leave it like that. I'll give you full credit for that. But if you're an algebra type, you want to simplify. Okay, and m divided by t squared L. Okay? So that's the dimension of pressure. How about density? Number 7. The definition of density. So the dimension of density, we look at the definition of density. It's the object's mass, so the dimension is mass, or m, and divided by the volume. Well, what's the dimension of volume? Well, we have volume is obtained by multiplying the length of the side of a box. Okay, width, depth, and height. It's width times depth times height. All of these dimensions, width, depth, and height are all measured with a ruler. So, okay, all measured with a ruler. So it's going to be length times length times length, or length cubed. So we have mass divided by length cubed. Okay? All right, so let me save this work. Okay, save that. And let me erase all this, and let me scroll this up. Oh, sorry. All right, so we did the density. Let's do power now. Okay, I'm going to go back to that. Power. What's the dimension of power? Well, it's how much energy is used. From step 5, I erased it, but let me put that back there. I have done this so many times, I've memorized the dimension of energy. It's ml divided by t squared. Ml squared divided by t squared. Right. So we're going to use that and put that into step question 8. Okay. We don't have to redo all this work. Use the work you've done before. Okay. So that comes in the numerator, ml squared divided by t squared. Okay, and then the denominator. What is the dimension of this quantity? Well, how long it took for something to happen. So that's how long it takes something to happen is measured with a stopwatch or a clock. So it's a time. Okay, and simplifying that, we get ml squared divided by t cubed. Right? Spring constant. What's the dimension of a spring constant? Okay. At this point, you don't even need to know what a spring constant is. Just follow the steps. Okay. Way up here, okay, I've scrolled out so I don't have it, but over here we determined the dimension of force. It was ml over t squared. I think it was in question 3. So we'll reuse this result. Bring it down here. So the numerator is a force. So it's ml divided by t squared. The denominator is how much does the spring stretch? What device would you use to measure this? How much does the spring stretch? Would you use a stopwatch? Would you use a bathroom scale? You would use something like this, a ruler, okay? And a ruler measures length. So we have L here, okay? And if you're the algebra type, simplify, and the L cancels out in the numerator and the denominator, so we have mass per time squared, okay? And that's your answer. Either form is okay. If you're not good at algebra, just leave it in the unsimple form. I'll give you full credit for that. Okay, final problem. It's a little bit of a twist. We have a new physical quantity. Amount of electric charge passing through a wire, okay, divided by how much time you gave it for the electricity to pass through. Okay, well, what's the dimension of electric charge? That's the weird one, where it was Q, okay, and the denominator is how much time. So of course it's T, and that's it. Q divided by T. I know it's complicated, or it's not really complicated. It's really simple, but I know it's abstract, and most of you freshmen, you're not used to thinking in abstract terms. And physics is the most abstract of the sciences. Okay. Mathematics is even more abstract than physics, but physics is the most abstract of the sciences. And if I didn't teach you this, you would never know that this is an important, this sort of mental process is an important part of what makes physics physics. Okay, so struggle through it, okay? Don't just give up, struggle with it. Try to wrap your mind around this weird, strange idea, and maybe a few years from now, you'll remember it and say, wow, oh, this is what Mr. Gilliam was talking about. All right, well, good luck, and I'll see you tomorrow.